This very second, you are traveling through time. Not metaphorically, literally. The clock on your wall ticks slower than clocks orbiting Earth in satellites. Your head ages faster than your feet by measurable amounts. Astronauts who spent a year on the International Space Station returned to Earth 13 milliseconds younger than they would have been if they stayed home. This is not science fiction. This is confirmed physics that governs every GPS satellite, calculating your location. But here is what will shatter your understanding of reality. Physicists have proven mathematically that traveling forward through time at accelerated rates requires nothing more than velocity or gravity. The equations work. The experiments confirm them. Yet traveling backward through time creates paradoxes so severe they might break the logical fabric of existence itself. We will explore the science that makes time machines theoretically possible, the paradoxes that make philosophers lose sleep, and the terrifying implications for free will if any of this proves achievable. If you want to understand why time travel might be the one frontier that reality itself forbids us to cross, please like and subscribe before we start our exploration. Make yourself comfortable. Let's begin. Every human who has ever lived experienced time as an arrow pointing in one direction. Birth leads to death. Causes precede effects. Tomorrow follows today with mechanical certainty. This felt experience of time as a river carrying us forward seems so fundamental to existence that questioning it feels absurd. You wake up, you live through the day, you go to sleep, and tomorrow arrives whether you want it to or not. The past recedes behind you like a landscape viewed from a departing train, becoming more distant with every passing moment, until it fades into memory and then into nothing at all. Yet physicists have known for over a century that this intuitive understanding of time is almost entirely wrong. The river of time that seems to carry you forward does not exist in the equations that describe reality at its most fundamental level. The sensation of now, this immediate present moment that feels more real than anything else in your experience, has no special status in the mathematics of space-time. Albert Einstein destroyed our comfortable assumptions about time in 1905 with his special theory of relativity. Before Einstein, scientists assumed that time flowed at the same rate everywhere in the universe. A second on Earth equaled a second on Mars equaled a second in the most distant galaxy, observable through the most powerful telescope. This assumption seemed so obviously true that nobody thought to question it seriously. Clocks measured time. Time was universal. Different clocks might be set to different hours, but they all ticked at the same rate. Case closed. Isaac Newton himself had codified this assumption 2 centuries earlier. In his masterwork, Principia Mathematica, Newton described absolute time flowing uniformly without relation to anything external. Time was a stage on which events played out, unchanging and unchanged by those events. The universe possessed a cosmic clock that ticked identically for all observers everywhere, providing a universal standard against which all motion and change could be measured. Einstein recognized something profound that his predecessors had missed entirely. The speed of light is absolute and unchanging, regardless of how fast you move. If you shine a flashlight while traveling at half the speed of light, that light beam does not travel at 1.5 times light speed relative to someone standing still. It travels at exactly light speed. Always. No matter what. No matter how fast you move. No matter which direction you travel. No matter who observes the measurement. This experimental fact had been established by Albert Michelson and Edward Morley in 1887. They attempted to measure Earth's motion through the hypothetical luminiferous ether, the medium that 19th century physicists believed carried light waves through space. Their experiment should have detected variations in light speed depending on Earth's direction of motion. It detected nothing. Light travelled at exactly the same speed, regardless of the direction of measurement. Most physicists of the era tried to explain away this troubling result with increasingly complex theories about how matter might contract in the direction of motion, hiding the expected speed variations. Einstein took a different approach. He accepted the experimental result at face value and asked what it implied about the nature of space and time themselves. This single observation about light speed unraveled everything humanity thought it knew about time. For the mathematics to work, for the speed of light to remain constant regardless of the observer's motion, something else must be variable. That something is time itself. Time is not a universal constant ticking away at identical rates across the cosmos. Time is personal. Time is relative. Time passes at different rates depending on how fast you are moving relative to other observers. The implications are staggering and deeply counterintuitive. Two synchronized clocks that start together, showing identical times, will show different times if one clock travels rapidly and then returns to the other. This is not a mechanical error in the clocks. This is not a failure of measurement or a trick of perception. This represents a fundamental property of space-time that Einstein discovered through pure mathematics and that scientists have since confirmed through countless experiments of ever-increasing precision. Scientists call this phenomenon time dilation. The faster you move through space, the slower you move through time relative to someone at rest. At everyday speeds, the speeds of cars and airplanes and even rockets, this effect is so tiny it cannot be detected without instruments capable of measuring billionths of a second. But as velocities approach significant fractions of light speed, time dilation becomes dramatic enough to notice without any instruments at all. Consider what this means for the fundamental nature of time. If two observers moving at different velocities genuinely experience time passing at different rates, not as an illusion but as physical reality, then there is no universal now connecting all points in the universe. The present moment that feels so immediate and obvious to you, this instant of reading these words, does not exist as a cosmic reality shared by all observers everywhere. Your now differs from the now experienced by someone traveling at high velocity, even if you are standing right next to each other at the moment of comparison. This sounds impossible. It sounds like a logical contradiction. How can two people standing in the same room experience different present moments? The resolution lies in recognizing that simultaneity itself is relative. Events that appear simultaneous to one observer appear to occur at different times to observers in different states of motion. There is no objective fact about whether two distant events happened at the same time. The question itself has no universal answer. Imagine a train passing through a station at high speed. A light flash occurs at the exact center of the train. From the perspective of a passenger on the train, the light reaches both ends of the train at exactly the same moment because the light travels equal distances in both directions. But from the perspective of an observer standing on the platform, the rear of the train moves toward the expanding light sphere, while the front of the train moves away from it. The light reaches the rear of the train before it reaches the front. Both observers are correct. There is no absolute fact about whether the light reached both ends simultaneously. Simultaneity depends on the observer's state of motion. This is not a matter of different perspectives on the same underlying reality. This is the underlying reality itself being different for different observers. This realization leads to one of the most disturbing concepts in modern physics. The block universe theory proposes that past, present, and future all exist simultaneously as a four-dimensional structure. Imagine the entire history of the universe from the Big Bang to the heat death of the cosmos laid out like a loaf of bread. Every moment that ever occurred and every moment that ever will occur exists as a slice within this four-dimensional block. From this perspective, time does not flow. Nothing moves through time. Instead, different moments simply exist at different locations within the block universe, just as different places exist at different locations in three-dimensional space. London and Tokyo both exist right now even though you can only be in one place. Similarly, yesterday and tomorrow both exist right now, even though you can only experience one moment. The past is not gone. The future is not waiting to happen. Both are as real as the present. They simply exist elsewhere within the four-dimensional structure of space-time. Your birth exists. Your death exists. Every moment of your life between those endpoints exists eternally within the block, as real and as permanent as any location in space. This sounds like philosophy rather than physics. It sounds like metaphysical speculation that could never be tested or confirmed, but the mathematics of relativity support this interpretation with disturbing consistency. If there is no universal now, if simultaneity depends on the observer's motion, then the distinction between past, present, and future becomes a matter of perspective rather than cosmic truth. Consider two observers, one on Earth and one in a spacecraft traveling away from Earth at high speed. Due to the relativity of simultaneity, events that lie in Earth observer's future might lie in the spacecraft observer's past, not because the spacecraft observer remembers those events, but because the geometry of space-time places those events in different temporal relationships relative to the two observers. If the past is real for one observer while being future for another, how can we maintain that only the present truly exists? The present moment has no privileged status in the physics. It is merely where each observer happens to be located within the four-dimensional structure. The sense that now is special, that the present is more real than the past or future, appears to be a feature of consciousness rather than a feature of physics. Einstein himself found this implication unsettling despite having discovered the physics that implied it. After the death of his close friend Michel Besso in 1955, Einstein wrote a letter to Besso's family containing a remarkable statement. He said that the distinction between past, present, and future is only a stubbornly persistent illusion. This was not poetic sentiment from a grieving friend seeking comfort in philosophy. This was Einstein stating what his own equations implied about the fundamental nature of temporal reality. Besso was gone from Einstein's present. But according to the physics Einstein himself had discovered, Besso still existed somewhere in the block universe, as real as he had ever been, simply located at temporal coordinates that Einstein could no longer access. The grief was real. The sense of loss was real. But the belief that Besso had ceased to exist was, according to the physics, an illusion created by human consciousness interpreting a four-dimensional reality through three-dimensional perception. But if the block universe model is correct, what does this mean for the possibility of time travel? If the past and future both exist as real locations within four-dimensional space-time, then traveling to them becomes conceptually similar to traveling to a different location in three-dimensional space. You cannot currently visit Tokyo if you're in London, but Tokyo nonetheless exists and could in principle be reached by appropriate means of travel. Similarly, yesterday exists and could in principle be reached if any physical process could move you along the temporal dimension rather than the spatial ones. The question shifts from whether time travel is logically possible to whether any physical mechanism could accomplish such travel. The past and future exist as destinations. The question is whether any vehicle could reach them. Before exploring that question, we need to understand how time dilation actually works in everyday circumstances. You do not need theoretical physics or thought experiments involving light beams and moving trains to observe relativistic effects. You interact with time dilation every single time you use a GPS navigation system on your phone. The Global Positioning System consists of approximately 30 satellites orbiting Earth at altitudes of roughly 20,000 kilometers. Each satellite carries atomic clocks precise enough to measure time to within billionths of a second. These clocks are not optional accessories. They are essential to the system's operation because GPS calculates your position by measuring how long radio signals take to travel from multiple satellites to your device. The calculation works through trilateration. If you know exactly when a satellite sent a signal and exactly when your device received it, you can calculate the distance to that satellite based on the speed of radio waves, which travel at light speed. Receive signals from 4 or more satellites, and you can pinpoint your position to within a few meters anywhere on Earth's surface. But this calculation requires extraordinarily precise timing. Radio signals travel approximately 300,000 kilometers per second. An error of just 1 microsecond in timing corresponds to a position error of 300 meters. The entire system depends on satellite clocks and ground clocks agreeing about what time it is to within nanoseconds. Here is where relativity becomes practical engineering rather than abstract theory. The satellites move at approximately 14,000 kilometers per hour relative to Earth's surface. Special relativity predicts that moving clocks run slower than stationary ones. At satellite velocities, this effect causes the onboard clocks to lose about 7 microseconds per day compared to identical clocks on Earth's surface. 7 microseconds sounds negligible. It is not. 7 microseconds of timing error would cause position errors of roughly 2 kilometers per day. Within a week, GPS would become useless for any practical navigation purpose. But there is a second relativistic effect, working in the opposite direction. General relativity, Einstein's theory of gravity published in 1915, predicts that clocks in weaker gravitational fields run faster than clocks in stronger gravitational fields. This is gravitational time dilation, separate from and additional to the velocity-based time dilation of special relativity. The GPS satellites orbit high above Earth where gravity is weaker than at the surface. Earth's gravitational field diminishes with distance according to the inverse square law. At 20,000 kilometers altitude, the gravitational acceleration is only about 6% of what it is at sea level. This weaker gravity causes the satellite clocks to run faster than ground-based clocks by approximately 45 microseconds per day. Combining both effects yields the net result. The velocity effect slows satellite clocks by 7 microseconds daily. The gravitational effect speeds satellite clocks by 45 microseconds daily. The net effect is that satellite clocks gain approximately 38 microseconds per day relative to clocks on Earth's surface. 38 microseconds per day. Light travels approximately 11 kilometers in 38 microseconds. Without corrections for relativistic time dilation, GPS position calculations would accumulate errors of roughly 10 kilometers per day. Within hours, the system would be noticeably degraded. Within a day, it would be worthless for navigation. GPS engineers must program relativistic corrections into the satellite clocks before launch. The onboard atomic clocks are deliberately set to tick at a slightly slower frequency than identical clocks on the ground. This pre-correction compensates for the relativistic speed-up the clocks will experience in orbit. Additional corrections are applied by the ground control system and by GPS receivers to account for smaller relativistic effects. The fact that GPS works proves that relativistic time dilation is real. This is not a theoretical prediction awaiting experimental verification. This is confirmed physics operating continuously in technology that billions of people rely on every day. Every time your phone accurately locates you, it confirms that Einstein was correct about the nature of time. Clocks in orbit tick at different rates than clocks on the ground. The difference is measurable, predictable, and must be compensated for in practical engineering applications. This brings us to a remarkable realization that should fundamentally change how you think about time travel. Time travel into the future is not theoretical speculation. It is not science fiction awaiting future technology. It is happening constantly to everyone and everything in the universe, based on relative motion and gravitational position. The effect is simply too small at everyday speeds and gravitational differences to notice without precision instruments. You do not feel yourself aging at a different rate than your neighbors because the differences amount to nanoseconds per day. But the GPS satellites orbiting overhead are genuinely traveling through time at a different rate than you are. They are aging slightly faster than you due to their weaker gravitational environment, even though they are also moving rapidly, which would cause them to age slower in isolation. Astronauts aboard the International Space Station experience both effects in combination. The station orbits at approximately 400 kilometers altitude, moving at roughly 28,000 kilometers per hour. The velocity effect dominates at this orbital configuration. Astronauts who spend 6 months on the station return to Earth having aged approximately 5 milliseconds less than they would have if they stayed on the ground. 5 milliseconds is not much of a time travel adventure, but it is real-time travel nonetheless. Those astronauts genuinely skipped 5 milliseconds into Earth's future. They are 5 milliseconds younger than they would otherwise be. The effect is tiny because orbital velocities are tiny compared to the speed of light, but the physics scales up without limit. What if we could amplify these effects? What if we could move fast enough or dive deep enough into a gravitational well that time dilation became dramatic rather than microscopic? What if we could skip years or centuries into the future rather than mere milliseconds? The mathematics of relativity provides clear answers to these questions. The faster you move, the more time slows down for you relative to observers at rest. The relationship follows a precise mathematical formula that physicists call the Lorentz factor. As you approach the speed of light, time dilation approaches infinity. From your perspective, any journey would seem nearly instantaneous, regardless of the distance traveled, though of course you could never actually reach light speed. Consider a thought experiment that physicists have analyzed extensively. A spacecraft accelerates at 1 standard gravity, the same acceleration you feel standing on Earth's surface. This would be comfortable for human passengers, feeling like normal Earth gravity throughout the journey rather than the crushing or floating sensations of higher or lower accelerations. Maintaining this constant acceleration, the ship would reach relativistic velocities within approximately 1 year of ship time. 1 year of continuous acceleration at 1 gravity brings you to approximately 77% of light speed. Continue accelerating, and you approach ever closer to light speed without ever reaching it. The energy required increases without limit, but the velocity continues climbing asymptotically toward that cosmic speed limit. After accelerating for 1 year of ship time, decelerating for 1 year to arrive at rest at your destination, then repeating the process for the return journey, the total trip from the traveler's perspective would last roughly 4 years, regardless of the destination. The travelers experience 4 years of time, but the distance they cross during those 4 years and the time that passes on Earth depends on how close to light speed they approached. A round trip to the nearby star Vega, located approximately 25 light-years from Earth, at constant 1 gravity acceleration would take approximately 12 years from the perspective of the crew. The journey out takes 6 years of ship time, 3 accelerating and 3 decelerating. The journey back takes another 6 years, 12 years total, but roughly 20 years would pass on Earth during their absence. The travelers would return to find that nearly twice as much time had passed for everyone they left behind. Friends would be older. Technology would have advanced, history would have unfolded. All while the travelers experienced only 12 years. Journey to the center of our galaxy, approximately 26,000 light-years distant, and the asymmetry becomes far more dramatic. The crew experiences perhaps 40 years of ship time. Earth experiences approximately 60,000 years. The travelers would return to find that human civilization had either transformed beyond recognition, spread across the galaxy, or vanished entirely. Nothing they knew would remain. The Earth itself might be unrecognizable. Its continents shifted, its climate altered, its dominant species evolved or replaced. These calculations are not speculation or approximation. The mathematics is precise, the physics is settled. Forward time travel at arbitrary rates requires nothing more than sufficient velocity. The engineering challenges are immense. The energy requirements are staggering. But no new physics is needed. Everything required is already contained in equations published over a century ago. This asymmetry between traveler time and stay-at-home time creates what physicists call the twin paradox. Imagine two identical twins born at the same moment. One twin remains on Earth while the other boards a spacecraft and travels at near light speed to a distant star before returning home. When the travelling twin returns, she has aged perhaps 5 years. Her sister, who stayed on Earth, has aged 50 years, or 500 years, or 5,000. The ratio depends entirely on how close to light speed the traveller approached. This seems to violate the principle that motion is relative. If all motion is relative, then the travelling twin can legitimately claim that she was stationary while the Earth moved away and then returned. From her perspective, she never moved at all. The universe moved around her. Should not both twins therefore age equally, each observing the other's clock running slow? The resolution lies in acceleration. The travelling twin experienced acceleration when leaving Earth, pushing her spacecraft up to near light speed. She experienced acceleration when turning around at the destination, reversing her direction of motion. She experienced acceleration when slowing down to return to Earth. These accelerations break the symmetry between the two reference frames in a way that has no ambiguity. Acceleration is absolute even when velocity is relative. You can always tell if you're accelerating by watching a mass on a spring or feeling pressure against your seat. The twin who felt these accelerations is unambiguously the one who travelled. The twin who felt no acceleration is unambiguously the one who stayed home. And the twin who accelerated is unambiguously younger upon reunion. The twin paradox is not actually a paradox at all, despite its name. It is a confirmed prediction of special relativity that has been verified experimentally multiple times with increasing precision as technology has improved. In 1971, physicists Joseph Hafele and Richard Keating performed one of the most famous tests of relativistic time dilation. They flew atomic clocks around the world on commercial aircraft, comparing them to reference clocks that remained stationary at the United States Naval Observatory. The travelling clocks showed time differences matching relativistic predictions within the experimental error bars. Clocks flown eastward, moving with Earth's rotation, showed different time shifts than clocks flown westward, moving against Earth's rotation. Both results matched theoretical predictions accounting for both velocity and gravitational effects. More dramatically, particle accelerators routinely demonstrate time dilation with subatomic particles that can be accelerated to velocities far exceeding anything achievable with human passengers. Muons provide particularly compelling evidence. These unstable particles are created in the upper atmosphere when cosmic rays strike air molecules. Muons have a half-life of approximately 2.2 microseconds, meaning that half of any population of muons will decay within that time. At this decay rate, muons created at the top of the atmosphere should disintegrate before reaching the ground. The atmosphere is roughly 100 kilometers deep. Even traveling at the speed of light, crossing this distance would take approximately 300 microseconds. During this time, the muon population should decay through more than 100 half-lives, reducing any initial population to effectively zero. Yet ground-based particle detectors observe abundant muons arriving from above. Far more muons reach the ground than the naive calculation permits. The explanation is time dilation operating at relativistic velocities. These atmospheric muons travel at roughly 99.9% of light speed, generated with enormous energies by cosmic ray collisions. At this velocity, time for the muon passes approximately 22 times slower than time for observers on the ground. From the muon's perspective, only a fraction of a half-life passes during the journey from upper atmosphere to surface. From our perspective, the muon survives far longer than it should because its internal clock runs slower than ours. Every experiment confirms the same conclusion with ever-increasing precision. Time is not absolute. Time passes at different rates depending on relative velocity and gravitational potential. The effect is real, measurable, and exactly as Einstein predicted. Forward time travel is not science fiction waiting for some future breakthrough. It is confirmed physics that operates continuously throughout the universe, whenever objects move relative to each other or occupy different gravitational potentials. But here is where things become genuinely strange. If time dilation allows traveling forward through time at accelerated rates, skipping years or centuries into the future by moving at high velocity, does the mathematics also permit traveling in the other direction? Can the equations that so accurately describe forward time dilation be reversed or modified to describe travel into the past? The answer depends entirely on what aspects of physics you are willing to consider and which theoretical possibilities you are willing to take seriously. General relativity. Einstein's theory of gravity permits mathematical solutions involving what physicists call closed time-like curves. These are theoretical paths through space-time that loop back on themselves, allowing an object to return to its own past. These solutions are mathematically valid within Einstein's equations. They satisfy all the mathematical requirements that valid solutions must satisfy. They represent possible configurations of space-time as far as the mathematics is concerned. But whether they represent physical possibilities that could actually exist in our universe, or merely mathematical artifacts without physical meaning, remains one of the most controversial and fascinating questions in all of theoretical physics. What we know with certainty is that time is far stranger than common sense suggests. The river flowing in one direction is an illusion. The universal, now connecting all observers, is a fiction. The clear distinction between past, present, and future may be nothing more than a stubbornly persistent illusion, as Einstein himself stated. We are all time travelers, moving forward through time at rates that depend on our motion and our position in gravitational fields. The technology to amplify this effect exists in principle within known physics. The paradoxes that arise when we contemplate traveling in the opposite direction will challenge everything you think you understand about causality, free will, and the nature of reality itself. The mathematics of time dilation follows a precise formula derived from Einstein's special theory of relativity. This equation, known as the Lorentz factor, determines exactly how much time slows down for a moving object compared to a stationary observer. The formula involves the ratio of the object's velocity to the speed of light, and as this ratio approaches 1, the time dilation factor climbs toward infinity along a curve that never quite reaches its asymptote. At 50% of light speed, time for the traveler passes at approximately 87% the rate of time for a stationary observer. The effect is noticeable but not dramatic. For every hour you experience aboard your spacecraft, roughly 69 minutes pass for observers who remained behind. Travel for a year at this velocity, and you return to find that approximately 14 months have elapsed on Earth. At 90% of light speed, time for the traveler passes at approximately 44% the rate of time for a stationary observer. Now, the effect becomes significant. For every hour of your subjective experience, more than 2 hours pass in the outside universe. A year of your life corresponds to more than 2 years passing for everyone you left behind. At 99% of light speed, time passes at roughly 14% the normal rate. 1 hour for you becomes 7 hours for external observers. 1 year of ship time corresponds to more than 7 years passing on Earth. At 99.9% of light speed, time slows to about 4.5% of the stationary rate. Your single year of experience stretches across 22 years of external time. These numbers reveal something remarkable about near light speed travel. The closer you approach light speed, the more dramatically time slows, following a mathematical curve that rises toward infinity without ever reaching it. Each additional 9 added after the decimal point multiplies the time dilation effect by roughly another factor of 3. At 99.99% of light speed, 1 year of your time corresponds to approximately 70 years externally. At 99.999%, a single year of ship time stretches across more than 2 centuries of external duration. At light speed itself, the equations predict that time would stop completely. The Lorentz factor becomes infinite. A photon traveling at light speed experiences no passage of time whatsoever. From the photon's perspective, if we can even meaningfully apply the concept of perspective to a massless particle, its entire existence from the moment of emission to the moment of absorption happens in a single instant, regardless of the distance travelled. A photon leaving the Andromeda galaxy travels for 2.5 million years from our perspective before reaching Earth. But from the photon's own reference frame, if such a thing can be said to exist, no time passes during this journey. The photon is emitted and absorbed in the same instant of its own existence. The 2.5 million years of travel time is entirely a feature of external observation, not internal experience. This is one of the reasons physicists state with confidence that massive objects cannot actually reach light speed. As an object accelerates, its kinetic energy increases, according to relativistic formulas that differ dramatically from the classical equations Newton developed. At low velocities, kinetic energy scales, with the square of velocity, just as Newton calculated. Double your speed, and you quadruple your kinetic energy. But as velocities become relativistic, approaching significant fractions of light speed, the energy required to accelerate further increases faster than velocity itself. The relationship follows the same Lorentz factor that governs time dilation. The energy required to push any massive object all the way to light speed becomes mathematically infinite. No finite amount of energy, no matter how large, can accomplish this acceleration for any object possessing even the tiniest amount of mass. This is not an engineering limitation that might be overcome with better technology. This is a fundamental feature of how space-time works. The speed of light is not merely very fast, it is a structural limit built into the geometry of the universe itself. Approaching it requires infinite energy, because reaching it would require leaving the domain where the equations of physics can describe your motion at all. But approaching light speed arbitrarily closely remains possible, at least in principle. Each increment of velocity toward light speed requires more energy than the previous increment. Following a curve that climbs steeply but never quite reaches the forbidden limit. With sufficient energy, a spacecraft could theoretically achieve 99.999% of light speed, where time would pass thousands of times slower than normal. Adding more nines requires exponentially more energy, but no physical law prevents it. Consider the practical implications for interstellar travel across the vast distances that separate stars from one another. Our nearest stellar neighbour, Proxima Centauri, lies approximately 4.2 light-years from Earth. This means that light itself, travelling at the absolute cosmic speed limit, requires more than 4 years to cross the gulf of empty space between our Sun and this small red dwarf star orbiting in the Alpha Centauri system. No spacecraft can travel faster than light. This is not a technological limitation, but a physical law as fundamental as conservation of energy. Therefore, any journey to Proxima Centauri must take at least 4.2 years, as measured by observers on Earth. The light travel time sets an absolute minimum for how quickly news of arrival could reach home. A spacecraft travelling at 99% of light speed would reach Proxima Centauri in roughly 4.24 years of Earth time, barely longer than the light travel time itself. The journey cannot happen faster than this regardless of technology or energy expenditure. But from the crew's perspective, time dilation compresses the subjective experience dramatically. Only about 7 months would pass inside the spacecraft during the entire voyage. The crew would experience less than a year of their own lives while Earth aged more than 4 years. This asymmetry between traveller time and external time represents genuine time travel into the future. The crew departs Earth in the year 2050, let us say. They experience 7 months of ship time, reading books, conducting experiments, watching the stars shift as they approach their destination. They arrive at Proxima Centauri and send a message home announcing their arrival. That message, travelling at light speed, takes 4.2 years to reach Earth. When it arrives, the calendar on Earth reads approximately 2058. More than 8 years have passed since the crew's departure. But the crew has aged only 7 months. They have effectively travelled 7.5 years into Earth's future while experiencing less than 1 year of subjective time. Journey to more distant destinations, and the asymmetry becomes more extreme with every additional light year of distance. The bright star Vega lies approximately 25 light years from Earth. A journey at 99.9% of light speed would take approximately 25 years of Earth time, but only about 14 months of ship time. The crew would return to find that half a century had passed while they experienced barely more than 2 years. The centre of our galaxy lies approximately 26,000 light-years away. At 99.99% of light speed, the journey would take approximately 26,000 years from Earth's perspective. Human civilization, as we know it, is only about 10,000 years old. The travellers would return to an Earth that had experienced nearly 3 times the entire span of recorded human history, but the crew themselves would have experienced only about 40 years of subjective time, less than half a human lifetime. The Andromeda Galaxy, our nearest major galactic neighbour, lies approximately 2.5 million light-years away. The light reaching your eyes from Andromeda tonight began its journey before the genus Homo existed on Earth. Any journey to Andromeda at subluminal velocities must take at least 2.5 million years from Earth's perspective. The civilization that launched the spacecraft would be ancient history before the travellers arrived, but a spacecraft maintaining 99.999% of light speed would allow the crew to experience the entire journey in approximately 50 years of subjective time. 50 years is a long voyage, but within a human lifetime. A young astronaut could depart Earth, cross the gulf between galaxies, and arrive at Andromeda as an elderly person still capable of exploring what they found. The return journey would take another 50 years of subjective time. The astronaut would return to Earth having aged approximately 100 years, perhaps with life extension technology keeping them alive for the complete round trip. But 5 million years would have passed on Earth. The continents would have shifted. Evolution would have transformed every species. Nothing recognizable would remain. In principle, sufficiently advanced spacecraft could traverse the entire observable universe within a single human lifetime of subjective experience. The observable universe measures approximately 93 billion light-years in diameter. At velocities asymptotically approaching light speed, a crew could cross this unimaginable distance while experiencing perhaps 70 or 80 years of ship time. The crew would emerge on the far side of the cosmos, having aged a single human lifetime, while billions upon billions of years passed in the universe around them. Everyone they ever knew would be dead. Every civilization that existed when they departed would be extinct or evolved beyond recognition. Every star that shone during their departure would have burned through its fuel, exploded, collapsed, or faded into cold darkness. The universe they entered would be unrecognizably different from the universe they left. This represents the true power and the true horror of relativistic time travel. The journey forward through time is effectively permanent and irreversible. You can skip forward through centuries or millennia of external time while experiencing only years or decades of subjective time. But you can never go back. The people and places you left behind age and change and eventually cease to exist while you coast through the cosmos at relativistic velocities. Return trips face the same asymmetry in the same direction. A traveller who journeyed 100 years into the future through near-light speed travel could theoretically make another journey by accelerating again to near-light speed. But this second journey would push them even further into the future, not back toward their origin time. Every relativistic journey adds to your temporal displacement. None subtract from it. Imagine departing Earth in the year 2100. You accelerate to 99.99% of light speed and coast for what feels like 2 years of ship time. You decelerate and check the calendar. Earth has experienced approximately 140 years. The year is now 2240. Everyone you knew is dead. The world has transformed in ways you cannot predict. You want to return to your own time, to see your family again, to live in the world you understood. But physics offers no path backward. You can only travel further forward. you could accelerate again, experiencing another 2 years of ship time while Earth ages another 140 years. You would arrive in the year 2380, even further removed from everything you knew. Or you could remain stationary, aging at the normal rate, watching the years pass one by one as the future unfolds around you. Either way, your past is gone. The year 2100 will never come again. Velocity is not the only pathway to dramatic time dilation. Gravity creates the same effect through a completely different physical mechanism, one that Einstein discovered when he extended his special theory of relativity to include gravitation. Einstein's general theory of relativity, published in 1915, describes gravity not as a force pulling objects together, but as curvature in the fabric of space-time itself, caused by the presence of mass and energy. Massive objects, like stars and planets, do not reach out and grab other objects through some invisible force. Instead, they bend the geometry of space and time around themselves, and objects moving through this curved geometry follow the straightest possible paths available to them. These straightest possible paths through curved space-time are called geodesics. A satellite orbiting Earth follows a geodesic, the straightest possible path through the curved space-time around our planet. From the satellite's perspective, it moves in a straight line. The curvature of space-time, caused by Earth's mass, makes this straight line loop back on itself, creating what we observe as an orbit. But general relativity's most startling prediction concerns time itself. The curvature of space-time affects not only the paths of objects follow through space, but also how time passes in different gravitational environments. Mass curves time as well as space. Clocks in stronger gravitational fields tick slower than clocks in weaker gravitational fields. This gravitational time dilation is separate from and additional to the velocity-based time dilation of special relativity. An object can experience both effects simultaneously if it is both moving rapidly and located in a gravitational field. The GPS satellites orbiting Earth experience both, with the gravitational effect actually dominating the velocity effect at their orbital altitude. The effect of gravitational time dilation is tiny at Earth's surface. Our planet is relatively small and not particularly dense by cosmic standards. The gravitational time dilation between sea level and the top of Mount Everest amounts to fractions of microseconds per year. Between sea level and orbital altitude, the effect reaches tens of microseconds per day, enough to matter for precision navigation but not enough to notice in human experience. But Earth's gravity is extraordinarily weak compared to other objects in the universe. Our planet's surface gravity accelerates falling objects at approximately 10 meters per second squared. The surface gravity of the Sun is roughly 28 times stronger. The surface gravity of a white dwarf star, the collapsed remnant of a sun-like star at the end of its life, can be 10,000 times stronger than Earth's. Near a neutron star, the collapsed core left behind after a massive star explodes as a supernova. Surface gravity becomes truly extreme. Neutron stars pack roughly 1.5 times the mass of our Sun into a sphere only 20 kilometers across, roughly the size of a city. The resulting surface gravity exceeds Earth's by a factor of approximately 200 billion. At this gravitational intensity, time dilation becomes measurable over periods as short as seconds rather than requiring years of accumulated effect. A clock on the surface of a neutron star would tick approximately 30% slower than an identical clock far from any gravitational source. 1 year of time experienced on the neutron star surface corresponds to roughly 1.4 years passing in distant flat space-time. But even neutron stars pale in comparison to the most extreme gravitational environments the universe provides. Black holes represent the ultimate triumph of gravity over all other forces. Objects so dense that space-time curves back on itself completely, preventing even light from escaping. Black holes form when massive stars exhaust their nuclear fuel and collapse under their own gravity. If the collapsing core exceeds approximately 3 solar masses, no known force can halt the collapse. The matter falls inward without limit, creating a singularity of theoretically infinite density surrounded by an event horizon, the boundary beyond which nothing can escape. The event horizon is not a physical surface. There is nothing material there that you could touch or see. It is simply the boundary where the escape velocity from the black hole's gravity equals the speed of light. Inside this boundary, escaping would require traveling faster than light, which is impossible. Therefore, anything crossing the event horizon is trapped forever. Near a black hole's event horizon, gravitational time dilation approaches infinity. The closer you get to the horizon, the slower your time passes relative to distant observers. At the horizon itself, the time dilation factor becomes mathematically infinite. From the perspective of a distant observer, objects approaching the horizon slow down asymptotically, never quite reaching it. Frozen in time against the black abyss, an observer falling into a black hole would experience something completely different. From their own perspective, they would cross the event horizon in finite proper time. Nothing special would happen at the moment of crossing. There is no wall, no barrier, no sensation marking the transition. The falling observer would continue falling toward the central singularity, where tidal forces would eventually stretch and compress them beyond survival, in a process physicists grimly call spaghettification. But an observer watching this fall from a safe distance would see something completely different. They would watch the falling observer approach the event horizon and slow down. The falling observer's clock would tick slower and slower relative to the distant observer's clock. The falling observer's image would redshift toward longer wavelengths as photons climbing out of the gravitational well-lost energy. The distant observer would never actually see the falling observer cross the event horizon. From the outside perspective, the falling observer would fade from view while appearing to hover just above the boundary. Frozen in time, redshifted through visible light into infrared, then into radio waves, then into wavelengths too long to detect. The falling observer would seem to take forever to reach the horizon, even though they experience the crossing in moments. This asymmetry creates remarkable possibilities for forward time travel, using gravity instead of velocity. A spacecraft orbiting close to a black hole's event horizon without crossing it would experience severe gravitational time dilation. The crew would live their lives normally from their own perspective, eating meals, conducting research, sleeping and waking. But time in the outside universe would race past at rates depending on how close their orbit approached the horizon. At a certain distance from the event horizon, 1 year of ship time might correspond to 10 years passing externally. Move closer, and 1 year corresponds to 100 years. Closer still, and 1 year corresponds to 1,000 years. In principle, there is no limit. An orbit skimming just above the event horizon could compress millions of years of external time into manageable durations of ship time. The film Interstellar depicted this phenomenon with reasonable scientific accuracy, consulting physicist Kip Thorne to ensure the gravitational physics was correct. Characters who descended to a planet orbiting extremely close to a supermassive black hole experienced roughly 1 hour of time, while 23 years passed for colleagues waiting in higher orbit. Every hour on the surface cost them decades of time in the outside universe. This ratio, while extreme, is physically plausible given sufficiently intense gravitational fields. The film's black hole, named Gargantua, was depicted as a supermassive black hole containing approximately 100 million solar masses. Such objects exist at the centers of large galaxies, including our own Milky Way. The black hole at our galactic center, called Sagittarius A star, contains approximately 4 million solar masses. Supermassive black holes provide the most extreme environments for gravitational time dilation anywhere in the known universe. These monsters contain masses equivalent to millions or billions of suns, compressed into regions comparable in size to our solar system. The space-time curvature near their event horizons creates time dilation effects that dwarf anything achievable through velocity alone. A spacecraft that could somehow maintain a stable orbit just above the event horizon of a supermassive black hole would require propulsion technology far beyond anything humanity can currently imagine. The gravitational gradients near the horizon create tidal forces that would tear apart any conventional spacecraft. The radiation environment from infalling matter, heating to billions of degrees, would be lethal many times over. But setting aside these engineering challenges, the physics permits astonishing feats of forward time travel. A crew waiting in such an orbit might experience a few months of subjective time while millions of years passed in the outside universe. Entire civilizations could rise and fall while the crew ate dinner. Species could evolve, flourish, and go extinct between their breakfast and their lunch. The gravitational time machine shares a crucial property with the velocity-based time machine. Both permit travel in only one direction. Both allow travelers to skip forward through external time at rates determined by their velocity or their proximity to massive objects. Every experiment ever conducted confirms this asymmetry. High-velocity particles in accelerators live longer than identical stationary particles, their internal clocks running slower as relativity predicts. Clocks at higher altitudes run faster than clocks at lower altitudes because they experience weaker gravitational fields. Clocks in orbit experience both effects, with results precisely matching relativistic calculations. Nothing in confirmed physics produces the reverse effect. There is no velocity that makes your clock run faster than external clocks. There is no gravitational environment where your time speeds up relative to distant observers. The asymmetry is fundamental to the mathematics of space-time geometry itself. The equations that describe time dilation contain terms that are always positive when calculated correctly, according to the standard formulation of relativistic physics. Negative time dilation, running time backward relative to external observers, does not emerge from any known physical principle. The formulas simply do not permit it. Forward time travel is therefore simply the normal passage of time as experienced by all matter in the universe, amplified through velocity or gravitational effects. You cannot choose to experience 10 years while 1 year passes on Earth. But you can choose to experience 1 year while 10 years pass on Earth by moving fast enough or diving deep enough into a gravitational well. The confirmed experiments supporting relativistic time dilation are numerous and precise beyond any reasonable doubt. The Hafele-Keating experiment demonstrated time dilation with clocks flown around the world on commercial aircraft. Particle accelerators have measured time dilation in unstable particles with accuracy exceeding 1 part per billion. The lifetimes of accelerated muons and pions and kaons match relativistic predictions to many decimal places. The Global Positioning System provides continuous real-world verification that relativistic time dilation is not merely a theoretical prediction, but a practical engineering concern. Every GPS receiver on Earth processes timing signals that have been corrected for both special and general relativistic effects. These corrections are not optional features that engineers added out of theoretical interest. Without them, the system fails. Navigation errors would accumulate to kilometers per day if relativistic effects were ignored. The continued successful operation of GPS represents ongoing experimental confirmation of relativistic time dilation operating continuously across millions of devices worldwide. Every time your phone locates you accurately, every time your car's navigation system guides you to your destination, every time an airplane uses GPS to land safely, the reality of time dilation is confirmed once again. Atomic clocks have been compared between different altitudes on Earth's surface, confirming gravitational time dilation even at the relatively weak gravitational intensity our planet provides. Clocks at higher altitudes run measurably faster than clocks at lower altitudes, exactly as general relativity predicts. The effect amounts to approximately 1 second gained for every 60 million years at the top of a tall mountain compared to sea level. The Gravity Probe A, experiment in 1976, launched a hydrogen maser atomic clock to an altitude of approximately 10,000 kilometers aboard a Scout rocket. The clock's frequency was compared via radio link to identical clocks on the ground throughout the flight. The results confirmed gravitational redshift predictions to within 70 parts per million, eliminating any reasonable doubt about the reality of gravitational time dilation. More recently, optical atomic clocks have achieved precision sufficient to detect gravitational time dilation across height differences of less than 1 meter. In 2010, physicists at the National Institute of Standards and Technology demonstrated that 2 clocks separated vertically by just 33 centimeters showed measurable time dilation effects. Your head ages faster than your feet by approximately 90 billionths of a second per year, due to the difference in gravitational potential across the height of your body. This sounds absurd. How can time pass at different rates across such tiny distances? But the physics is unambiguous, and the measurements are precise. Time genuinely flows at different rates at different heights in a gravitational field. The effect is far too small to notice in human experience, but real enough to measure with sufficiently sensitive instruments. The precision of these experiments leaves no reasonable scientific doubt about the reality of time dilation in both its forms. Forward time travel is confirmed science, not speculation, not theory awaiting verification, but established fact supported by countless experiments across more than a century of physics. The only questions remaining about forward time travel are practical, rather than theoretical. How fast can we actually accelerate spacecraft with foreseeable technology? How close can we actually approach massive objects without being destroyed by tidal forces or radiation? What would motivate humanity to undertake journeys that would permanently separate travelers from everyone and everything they have ever known? These are questions of engineering, economics, and psychology rather than physics. The physics is settled. Relativity permits forward time travel at arbitrary rates. The universe places no theoretical limit on how far into the future you could travel, with sufficient velocity or sufficient gravitational time dilation. Whether anyone would choose such a journey, whether any civilization would invest the resources required, whether any human psyche could withstand the isolation, these remain open questions. But the physics gives permission. Yet forward time travel, however confirmed and however dramatic in its possibilities, represents only half of the time travel puzzle that has fascinated humans for generations. The truly mind-breaking questions arise when we consider the opposite direction. Can we travel backward through time? Can we visit the past, witness historical events, walk among ancestors who died before our birth? Can we change the past, alter decisions, prevent tragedies, reshape history according to our present desires? Here is where physics shifts from confirmed experimental results to theoretical speculation, from established fact to mathematical possibility fraught with logical paradox. The equations of general relativity permit certain exotic solutions that would theoretically allow what physicists call closed time-like curves, paths through space-time that loop back on themselves. If such curves exist in physical reality, an object following one would return to its own past, having genuinely travelled backward through time. Kurt Gödel, the brilliant mathematician famous for his incompleteness theorems, discovered the first such solution in 1949. Gödel described a rotating universe, where the rotation of all matter creates frame-dragging effects that allow closed time-like curves. In Gödel's universe, you could travel in a sufficiently large circle and return not only to your starting point in space, but to your starting point in time as well. Other theoretical solutions followed. The Tipler cylinder describes an infinitely long, extremely dense rotating cylinder whose frame-dragging effects would create closed time-like curves near its surface. Wormholes, hypothetical tunnels connecting distant points in space-time, could potentially be transformed into time machines if one end were accelerated to relativistic velocities and then returned. Cosmic strings, theoretical defects in space-time left over from the early universe, might permit backward time travel if two such strings passed each other at high velocity. The grandfather paradox presents the most famous logical problem created by backward time travel. Yet it has tormented physicists and philosophers for over a century because no one has ever produced a fully satisfying resolution. You build a time machine. You travel back in time to 1925, before your grandfather met your grandmother. You find your grandfather as a young man and kill him. Perhaps you shoot him. Perhaps you push him in front of a train. Perhaps you simply ensure he never attends the dance where he would have met the woman who became your grandmother. The method does not matter. What matters is that you succeed. Your grandfather dies before producing any offspring. This single action creates a cascade of consequences that ripple forward through time. Your grandfather never meets your grandmother. They never marry. They never have children. Your father or mother, whichever parent descended from this grandfather, is never born. And if your parent was never born, then you were never born either. But here is where the logical nightmare begins. If you were never born, then you never existed to build a time machine. You never travelled back to 1925. You never killed your grandfather. Your grandfather therefore survives. He meets your grandmother at that dance. They marry, have children, and eventually your parent is born. Your parent grows up, meets your other parent, and eventually you are born. But now you exist again. You build your time machine. You travel back to 1925. You kill your grandfather. He dies without offspring. Your parent is never born. You are never born. You never build the time machine. You never travel back. Your grandfather survives. Your parent is born. You are born. You build the time machine. You travel back. You kill your grandfather. The sequence loops endlessly, with no stable resolution. Each state creates the conditions that produce the opposite state. Your grandfather is both dead and alive depending on where you enter the loop. You both exist and do not exist. The past is both changed and unchanged. Every statement about what happened contains its own contradiction. This logical loop has no resolution within classical logic. The event of killing your grandfather creates the conditions that prevent you from existing to kill your grandfather, which allows your grandfather to survive, which allows you to exist, which allows you to kill your grandfather. The sequence cannot be assigned a consistent truth value. It cannot have happened and simultaneously not happened, yet both outcomes seem to follow necessarily from the premises you began with. The grandfather paradox is not merely a philosophical puzzle. It represents a genuine crisis for any physics that permits backward time travel. Physical theories must be logically consistent. They cannot permit states that contradict themselves. If backward time travel creates unavoidable logical contradictions, then backward time travel must be impossible regardless of what any equation seems to permit. Physicists and philosophers have proposed various resolutions to the grandfather paradox over the decades since it was first clearly formulated. None of these resolutions is entirely satisfying. Each solution either introduces new problems, as troubling as the original paradox, requires abandoning cherished assumptions about the nature of reality, or simply declares the paradox impossible without providing any mechanism that would prevent it. The most straightforward resolution is brutally simple. Backward time travel is physically impossible. The grandfather paradox demonstrates a logical contradiction, and logical contradictions cannot occur in physical reality. Therefore, whatever physical laws govern our universe must prohibit the construction of time machines capable of traveling to the past. The mathematical solutions to Einstein's equations that seem to permit closed time-like curves must be physically unrealizable, perhaps due to quantum effects or energy constraints, or some mechanism we have not yet discovered. This resolution has considerable appeal because it preserves logical consistency without requiring exotic modifications to our understanding of reality. The universe simply does not permit backward time travel because backward time travel creates impossible situations. The mathematics of general relativity that permits closed time-like curves must be incomplete. or must describe mathematical possibilities that can never correspond to actual physical systems. Stephen Hawking formalized this approach in 1992 with what he called the chronology protection conjecture. Hawking proposed that the laws of physics conspire to prevent the creation of closed time-like curves through some mechanism that we have not yet fully understood. He noted that whenever physicists examine specific proposals for time machines in detail, something always seems to go wrong. Quantum effects destabilize wormholes. Energy requirements become infinite. Feedback loops destroy the machinery before it can function. Hawking famously quipped that we have strong experimental evidence for the chronology protection conjecture in the simple observation that we have never been invaded by tourists from the future. If backward time travel were possible, and if any civilization anywhere in the universe's future ever developed the technology, we might expect at least some temporal visitors to appear at historically significant events. The absence of obvious time travelers suggests that backward time travel never becomes possible regardless of how advanced technology becomes. But this resolution feels deeply unsatisfying to many physicists, despite its logical appeal. It invokes an unknown protection mechanism without specifying what that mechanism might actually be. It assumes that logical paradoxes somehow translate into physical impossibilities without explaining the precise connection between logic and physics. And it leaves completely unexplained why the mathematics of general relativity, our best theory of gravity, permits solutions that can never correspond to anything in physical reality. If general relativity permits closed time-like curves but the universe forbids them, then general relativity must be wrong or incomplete in some important way. This is not a shocking conclusion, since we already know that general relativity conflicts with quantum mechanics, and that some more complete theory must eventually replace both. But simply declaring that the time machine solutions are unphysical, without identifying the error, feels more like admitting defeat than providing an answer. A second resolution takes a radically different approach. It proposes that backward time travel is indeed possible, but that paradoxes are not. This is the Novikov self-consistency principle, developed by Russian physicist Igor Novikov in the 1980s and refined in subsequent decades. Novikov proposed that any action taken by a time traveler was always part of history. You cannot change the past because the past already includes whatever effects your time travel will eventually create. History is not a sequence of events that you can revise by traveling backward and making different choices. History is a fixed, four-dimensional structure that already incorporates every instance of time travel that will ever occur. Under this principle, if you travel back in time intending to kill your grandfather, something will prevent you from succeeding. Every single time. Without exception, your gun will jam at the critical moment. Your bullet will miss despite perfect aim. You will have an unexpected change of heart when you see his young face. You will get lost on the way to find him. You will be struck by a car before you reach him. The police will arrest you on an unrelated charge. A million possible interventions might occur, but something will always intervene because your grandfather did not die before having children. That is an established fact of history. Nothing you do can alter an established fact. The circumstances of the universe will conspire to ensure that your time travel creates no paradoxes because the timeline was always self-consistent. You were always going to travel back to 1925. You were always going to attempt to kill your grandfather. You were always going to fail. These facts were built into the structure of space-time from the beginning. Your experience of choosing to kill him and your experience of failing were always part of what happened. There is no alternate version of events where you succeed because there is only one version of events and your grandfather survived in it. This might seem like an absurd restriction on free will. It suggests that the universe somehow knows what you intend to do and arranges circumstances to prevent paradoxical outcomes. How can physical law constrain your choices in such a targeted way? How can mere physics know that a particular bullet must miss while another bullet could hit? The question seems to require cosmic intelligence or supernatural intervention. But Novikov's principle does not actually require such knowledge or intervention. It simply observes a logical constraint on what kinds of sequences of events are possible. Self-consistent timelines are logically possible. Paradoxical timelines are not. If backward time travel exists in a single fixed timeline, then only self-consistent sequences of events can occur. Paradoxical sequences are not prevented by some cosmic mechanism watching over causality. Consider an analogy from geometry. You cannot draw a square circle, not because some force prevents you from drawing one, not because the universe watches your pencil and intervenes, but because the concept of a square circle is self-contradictory. A square has 4 corners and straight sides. A circle has no corners and curved sides. No shape can simultaneously have both properties. Square circles do not exist among the set of possible shapes because the definition excludes them. Similarly, paradoxical time loops do not exist among the set of possible event sequences. A sequence where you kill your grandfather and therefore are never born to kill your grandfather is not prohibited by some mechanism. It is simply undefined. It is not a possible sequence of events in the same way that a square circle is not a possible shape. The Novikov principle does not describe a force that prevents paradoxes. It describes a logical constraint that excludes paradoxes from the space of possibilities, but Novikov's principle creates its own deeply disturbing implications that many find as troubling as the original paradox. If every action a time traveler takes was always part of history, then free will becomes illusory in a profound and perhaps terrifying sense. The time traveler cannot choose to create a paradox. Their choices are constrained in advance to produce only self-consistent outcomes. The universe appears to guide events toward consistency through mechanisms that look exactly like fate or destiny. You experience yourself as making a choice to pull the trigger. You feel the intention, the decision, the act of will, but your gun jams. You did not choose for the gun to jam. That was not your decision, yet it happened precisely because of what you chose to do, and it was always going to happen, and there was never any possibility of it not happening. Your choice was real as an experience, but illusory as an effective cause. You were going to fail from the beginning of time. This predetermined consistency raises deep questions about the nature of causality itself. In self-consistent time loops, effects can precede their causes in subjective time while remaining causally connected through the loop structure. A time traveler might receive information about the future, act on that information, and thereby cause the very events that led to the information being sent back. The causal loop is closed and self-consistent, but the arrow of causation no longer points in a single temporal direction. Which came first? The information or the events the information described? Neither. Both. The question itself becomes meaningless within a closed causal loop. The information and the events cause each other in a circular structure with no beginning and no end. Our usual intuitions about causality, about earlier events causing later events in a linear chain, break down completely. The bootstrap paradox illustrates this breakdown of causal intuition more vividly than any other thought experiment. The name comes from the impossible act of lifting yourself by pulling on your own bootstraps. Consider the following scenario that appears in countless science fiction stories because of how effectively it demonstrates the problem. You are a great admirer of Shakespeare. You travel back in time to 1600, the height of Shakespeare's career. You bring with you a beautiful leather-bound volume containing the complete works of Shakespeare, all 37 plays, all 154 sonnets, all the poems. You find the young playwright William Shakespeare in London and give him this book as a gift from an admirer. Shakespeare is astonished by the quality of these works. They are far better than anything he has written himself. Being a practical man of the theatre, he copies them out in his own hand and presents them as his own. The plays are performed, they are published, they become immortal classics that will be celebrated for centuries. You return to your own time, you visit the library, You check out a beautiful edition of the complete works of Shakespeare. You note that it contains the same 37 plays, the same 154 sonnets, the same poems. You take this book and travel back to 1600 to give it to Shakespeare. The loop is closed. The timeline is self-consistent. No paradox occurs in the sense of logical contradiction. Shakespeare published the plays. You obtained a copy of the plays. You gave the plays to Shakespeare. He published them. The sequence is perfectly consistent, even though it forms a closed loop in time. But now, ask the question that should trouble you deeply. Who wrote Shakespeare's plays? Not Shakespeare. He merely copied them from the book you gave him. He did not create them through any act of literary genius. He was a plagiarist, albeit an unwitting one who believed the works came from some future admirer with prophetic knowledge of his potential. But you did not write the plays either. You merely transported them from a library to 16th century London. You have no literary genius. You could not have composed Hamlet or King Lear or A Midsummer Night's Dream. The plays were never written by anyone. They exist in a closed causal loop with no point of origin. There was no moment of creation. There was no inspired author wrestling with language and meaning to produce these masterpieces. The works simply exist because they exist. They maintain themselves through the closed time-like curve. They bootstrap their own existence into reality. This violates our deepest intuitions about causality requiring prior causes. Everything that exists, we naturally believe, must have come from somewhere. Everything that was created must have had a creator. Every effect must have a cause that preceded it in time. The bootstrap paradox suggests that these intuitions are simply wrong if backward time travel is possible. Information and objects could exist without ever being created. Self-consistent loops would sustain stable structures of matter and knowledge that owe their existence to nothing but their own circular causation. The complete works of Shakespeare could exist without Shakespeare ever having written them. A time machine could exist without anyone ever having invented it, if a working model was sent back from the future to inspire its own creation. Some physicists find the bootstrap paradox even more disturbing than the grandfather paradox, precisely because it does not create logical contradictions. The grandfather paradox at least has the decency to be impossible. It refutes itself. You can point to the logical error and declare that such sequences cannot occur. The bootstrap paradox is logically consistent. It could occur. And it suggests that backward time travel would make causality fundamentally different from anything we experience in everyday life. Objects would not need origins. Events would not need causes. The universe would contain self-sustaining loops of matter, energy, and information that emerged from nowhere and owe their existence to nothing. The arrow of causation would not point from past to future, but would curve back upon itself in circles that have no beginning. The predestination paradox adds yet another layer of troubling complexity to the analysis of backward time travel. In this scenario, attempting to prevent an event through time travel causes the very event you are trying to prevent. Your intervention does not change the past. Your intervention is the past. What you experienced as a choice to alter history was always the mechanism by which history occurred. Greek mythology contains perhaps the most famous example of predestination logic. According to the legend, King Laius and Queen Jocasta of Thebes receive a prophecy that their newborn son will one day kill his father and marry his mother. Horrified by this prediction, they order a servant to abandon the infant on a mountainside to die. They believe that by eliminating their son, they can prevent the prophecy from being fulfilled. But the servant takes pity on the infant and gives him to a shepherd from the neighbouring kingdom of Corinth. The child, named Oedipus, grows up as the adopted son of the Corinthian king and queen. He believes they are his biological parents. He has no idea of his true origin. As a young man, Oedipus hears a rumour that he is adopted. He consults the oracle at Delphi, who tells him the same prophecy his biological parents received. He will kill his father and marry his mother. Horrified, Oedipus resolves never to return to Corinth, lest he harm the people he believes to be his parents. Travelling away from Corinth, Oedipus encounters an older man at a crossroads. They quarrel over who has the right of way. In the ensuing fight, Oedipus kills the older man. He does not know that this stranger is King Laius, his biological father. Oedipus continues to Thebes, which is being terrorized by a monster called the Sphinx. He solves the Sphinx's riddle and saves the city. As a reward, he is made king and given the widowed Queen Jocasta as his wife. He does not know that she is his biological mother. The prophecy is fulfilled. Oedipus has killed his father and married his mother, and the actions that led to this fulfillment were precisely the actions taken to prevent it. If Laius and Jocasta had not abandoned their son, he would have grown up knowing his true parents and would never have killed his father in an anonymous roadside quarrel or married his mother without recognizing her. The attempt to prevent the prophecy caused the prophecy. The predestination paradox creates no logical contradictions. The causal loop is self-consistent in the Novikov sense. Everything that happened was always going to happen. No impossible states are created. But the implications for free will and human agency are profound and disturbing. If time travelers cannot change fixed events, and if their attempts to change these events actually cause them, then the appearance of choice is purely illusory. Oedipus experienced himself as making decisions. He chose to flee Corinth. He chose to fight the stranger at the crossroads. He chose to accept the crown of Thebes and the queen's hand. Each choice felt real in the moment of making it. Each choice was meaningless in the actual unfolding of events. Time travelers in this framework are actors performing a script that has already been written. They experience agency. They feel themselves deliberating and deciding. But their lines are fixed. Their blocking is predetermined. They cannot improvise regardless of their subjective experience of making decisions. The script includes their sense of making choices. The script even includes their sense that they might have chosen differently. But the script was never going to be different, because there is only one script, and it already includes everything that will ever happen. Now consider what the actual physics of general relativity says about the possibility of backward time travel. Einstein's field equations describe how mass and energy curve the geometry of space-time. Given a distribution of matter and energy, the equations specify what the resulting space-time geometry must be. These equations permit mathematical solutions called closed time-like curves, world lines through space-time that loop back to their own starting points in time. The first such solution was discovered by the mathematician Kurt Gödel in 1949. Gödel, already famous for his incompleteness theorems that revolutionized mathematical logic, turned his attention to cosmology and asked whether Einstein's equations permitted time travel. Gödel described a model universe that rotates as a whole. All the matter in this universe participates in a slow, cosmic rotation around a common axis. The rotation creates a phenomenon called frame dragging, where space-time itself is twisted by the rotating matter. In Gödel's rotating universe, frame dragging becomes so severe that closed time-like curves emerge. An observer could travel in a sufficiently large circle and return not just to their starting point in space, but to their starting point in time. They would meet their own past self departing on the journey they just completed. Gödel's universe does not describe our actual cosmos. Astronomical observations confirm that our universe does not rotate globally. There is no preferred axis around which all matter revolves. The cosmic microwave background radiation is uniform in all directions to a high degree of precision, which would not be the case in a rotating universe. But Gödel's solution proved something important about general relativity itself. Einstein's equations permit closed, time-like curves in principle. The mathematical structure of relativity does not automatically exclude backward time travel. If closed time-like curves exist anywhere in the solution space of Einstein's equations, then the physics of gravity alone does not forbid time travel. Some additional principle must be invoked to exclude these solutions from physical reality. Other solutions permitting closed time-like curves followed Gödel's discovery. In 1974, the physicist Frank Tipler described a hypothetical structure now called the Tipler cylinder. This is an infinitely long, extremely dense cylinder, rotating at tremendous speed. The frame dragging effects near such a cylinder would create closed time-like curves in the surrounding spacetime, allowing backward time travel for observers who flew the correct trajectories near the cylinder's surface. The Tipler cylinder cannot be physically constructed because it must be infinitely long. A finite cylinder, no matter how long, would not produce the required frame dragging effects. The solution is mathematically valid, but physically unrealizable. Wormholes provide another theoretical pathway to the past that has received enormous attention from physicists and science fiction authors alike. A wormhole is a hypothetical tunnel connecting two distant points in space-time. Like a shortcut through the higher dimensional space in which our three-dimensional space is embedded, a wormhole could allow travel between points far more quickly than light traveling through normal space. If traversable wormholes exist, they could potentially be transformed into time machines through a straightforward application of special relativistic time dilation. Take one end of a wormhole and accelerate it to near light speed. Carry it on a long journey at relativistic velocity, then return it to its starting location. Time dilation will have caused the moving end to age slower than the stationary end. The two mouths of the wormhole now exist at different times, despite being at the same location in space. Step through the stationary mouth and emerge from the moving mouth. You have travelled backward in time by the amount of the time dilation difference. Return through the moving mouth and emerge from the stationary mouth in your original time frame. But wormholes present enormous theoretical and practical challenges that may prove insurmountable. Maintaining a traversable wormhole appears to require exotic matter with negative energy density. This is matter that gravitates repulsively rather than attractively. Matter with properties that no known substance possesses. Exotic matter may not exist anywhere in our universe. If it does exist, we have no idea how to obtain it, concentrate it, or manipulate it for engineering purposes. The energy requirements for creating and maintaining a wormhole appear to exceed the total energy output of entire stellar civilizations. Even if exotic matter exists and can be manipulated, gathering enough of it to hold open a traversable wormhole might require more energy than humanity could generate in millions of years of technological development. Moreover, there are strong theoretical reasons to believe that wormholes would be fundamentally unstable. Quantum effects might cause any forming wormhole to collapse before anything could pass through it. Virtual particles from the quantum vacuum would fall into the wormhole, accumulate at its throat, and create a feedback loop that destroys the structure. The chronology protection conjecture suggests that nature deploys such mechanisms wherever closed time-like curves threaten to form. The Alcubierre warp drive presents yet another approach to faster-than-light travel that has implications for backward time travel. In 1994, the physicist Miguel Alcubierre demonstrated that general relativity permits solutions where a bubble of flat spacetime moves through the surrounding space at arbitrarily high velocities, including velocities exceeding the speed of light. An object inside the Alcubierre bubble would not actually move faster than light relative to its local spacetime. Special relativity's prohibition on faster-than-light travel applies to motion through spacetime, not to the motion of spacetime itself. The bubble contracts space ahead of it and expands space behind it, essentially falling forward through a wave of spacetime distortion that carries it along. The Alcubierre drive does not directly enable backward time travel. The object inside the bubble experiences time normally while traveling to distant destinations in short periods of external time. But any mechanism that permits faster-than-light travel also permits travel to the past according to special relativity. This follows from the relativity of simultaneity. Events that appear to occur at the same time to one observer appear to occur at different times, to observers in different states of motion. Two observers moving relative to each other will disagree about which distant events are happening now. If faster than light signals or transport is possible, this disagreement can be exploited to send messages or travelers backward in time. The details involve constructing specific trajectory combinations, but the principle is straightforward. An observer could travel faster than light to a distant location, hand off information to a second observer moving rapidly relative to the first, and that second observer could use faster than light travel to reach the first observer before the original transmission occurred. The net effect is information, or matter, arriving before it departed. All of these theoretical mechanisms face the same fundamental question that has occupied physicists for decades. Do closed time-like curves represent physical possibilities that nature actually permits? Or are they mathematical artifacts that Einstein's equations allow, but that some deeper principle of physics excludes from reality? The honest answer is that we do not know. General relativity is known to be incomplete. It does not incorporate quantum mechanics, and any complete theory of gravity must eventually unify relativistic spacetime geometry with quantum physics. The theories being developed to achieve this unification, string theory, loop quantum gravity, causal set theory, and others, might eliminate closed time-like curves from the set of physical possibilities entirely. We currently lack the theoretical framework to answer with confidence, but even if physics ultimately permits backward time travel through some mechanism we can construct, the paradoxes we have examined remain. They do not disappear just because the physics works out. How do we resolve the grandfather paradox if time machines actually exist? Do we accept the Novikov self-consistency principle and its troubling implications for human free will? Do we embrace the bootstrap paradox and accept that objects and information can exist without any origin or creator? Do we invoke some unknown chronology protection mechanism that prevents paradoxes from ever arising regardless of what the physics permits? Each resolution to the paradoxes of backward time travel carries costs that many find unacceptable. Each challenges assumptions we hold dear about the fundamental nature of reality, about causality and its direction, about human agency and the meaningfulness of our choices. And there is one more resolution we have not yet discussed. It is perhaps the most disturbing of all, because of what it implies about the nature of existence itself. The many worlds interpretation of quantum mechanics offers the most radical solution to time travel paradoxes ever proposed by serious physicists. Originally developed by physicist Hugh Everett in 1957, to address fundamental problems in quantum mechanics that had nothing to do with time travel, this interpretation has since been adapted to explain how backward time travel might work without creating the logical contradictions that seem to make such travel impossible. To understand the many worlds solution to time travel paradoxes, you must first understand what the interpretation claims about the nature of reality itself. The claim is extraordinary. It suggests that our universe is not the only universe, that reality branches continuously into countless parallel versions of itself, and that every possible outcome of every quantum event actually occurs somewhere in this vast branching structure of alternate realities. In quantum mechanics, particles exist in superpositions of multiple states until they are measured or observed. An electron can be spinning clockwise and counterclockwise simultaneously. A photon can be polarized vertically and horizontally at the same time. A radioactive atom can be both decayed and not decayed until something interacts with it to determine which state it occupies. The traditional Copenhagen interpretation of quantum mechanics states that measurement causes this superposition to collapse into a single definite state. Before you look, the electron is spinning both ways. After you look, it is spinning only one way. The act of observation somehow selects one outcome from among the possibilities and makes it real while eliminating the others. This interpretation troubled many physicists because it seemed to give observers a special role in determining physical reality. Can a mechanical detector collapse a wave function, or must a human mind be involved? The Copenhagen interpretation never answered these questions satisfactorily. Hugh Everett proposed a radical alternative. What if all the possible outcomes of every quantum measurement actually happen, but in separate branches of reality that cannot interact with each other? The superposition does not collapse. Instead, the universe splits. When you measure whether an electron is spinning clockwise or counterclockwise, the universe divides into two branches. In one branch, you observe clockwise spin. In the other branch, you observe counterclockwise spin. Both observations actually occur. Both branches are equally real. You simply find yourself in one branch experiencing one outcome, while another version of you in the other branch experiences the opposite outcome. This happens not just for electrons in laboratories, but for every quantum event everywhere in the universe at every moment. Every radioactive decay, every photon absorption, every molecular interaction involves quantum probabilities that resolve into actual outcomes. In the many worlds interpretation, every possible resolution occurs. The universe branches exponentially, splitting into countless parallel realities every instant. The number of branches is beyond astronomical. Every second, countless quantum events occur throughout the observable universe. Each event that could have multiple outcomes generates branches for every possibility. The total number of branches that exist grows exponentially from an already incomprehensibly vast starting point. There are more branches of reality than atoms in the observable universe, by factors that require scientific notation with exponents in the exponents to express. Now apply this framework to the problem of time travel and the grandfather paradox. When you travel back in time and kill your grandfather, you do not create a logical contradiction. Instead, you create a new branch of reality, a branch that did not exist before your intervention but that becomes as real as any other branch once your time travel creates it. In the original branch of reality, your grandfather survived his youth. He met your grandmother. They married and had children. Your parent was born, grew up, met your other parent, and eventually you were born. You grew up, became interested in time travel, built a time machine, and traveled back to 1925. All of this happened in a single coherent timeline with no contradictions. When you arrive in 1925 and kill your grandfather, you do not erase this original timeline. The original branch continues to exist exactly as it always did. Your grandfather survived in that branch. Your parent was born in that branch. You were born in that branch. You departed in the time machine from that branch. That history remains fixed and unchanged. But your act of killing your grandfather creates a new branch that splits off from the original timeline at the moment of your intervention. In this new branch, your grandfather dies young. He never meets your grandmother. Your parent is never born. You are never born in this branch. But your existence in this new branch is not contradicted because you did not originate in this branch. You came from a different branch. The original branch where your grandfather survived. You are a visitor from another timeline. Your presence in the new branch is explained by your departure from the old branch. The causal chain that led to your existence is intact in your home branch. The new branch simply never contained a version of you that was born there. It contains only the version of you that travelled there from elsewhere. The grandfather paradox dissolves entirely under this interpretation. You cannot change your own past because your own past exists in a branch that your time travel does not affect. Every apparent change to history creates a new branch while leaving the original branch untouched. The past you came from is safe. It is just no longer accessible to you. This resolution eliminates logical contradictions at the cost of multiplying realities beyond imagination. Every time traveler creates new branches with every intervention. Every choice they make in the past spawns additional branches for every possible outcome of that choice. the branching structure of reality grows ever more complex with every temporal journey. But this solution comes with costs that some philosophers and physicists find more disturbing than the original paradoxes it resolves. If time travel creates new timeline branches rather than modifying a single timeline, then the past you visit is not actually your past. The people you meet there are not the people who shaped your life. They are alternate versions existing in a separate branch of reality. They look identical, they have the same memories up to the point of branching, but they are not the same individuals. If you travel back in time to save your mother from a car accident that killed her when you were young, you cannot actually save your mother. You can save a version of your mother in a newly created branch. Your actual mother died in your original branch, and that death remains unchanged. The woman you save is genetically identical, has the same memories, the same personality, the same love for you, but she is not the woman who gave birth to you. That woman died years ago in a branch you can never return to. You can never go home again. Every trip to the past moves you to a new branch. Every return to the future moves you to whatever future that new branch generates. Your original timeline, the world you grew up in, the people you knew, continues to exist, but is forever beyond your reach. Time travel under the many worlds interpretation is a one-way journey into an endless series of alternate realities. The implications multiply disturbingly when you consider what this means for the broader structure of reality. If backward time travel is possible and creates new branches, then travelers from countless future timeline branches might be visiting the past constantly. Every moment of history might receive visitors from multiple divergent futures, each visit creating additional branches, each branch generating its own future. Time travelers who visit their own pasts and create still more branches. We would never notice these visitors because they would disappear into their newly created branches, leaving our timeline unaffected. The tourist from the future who arrives in 1963 does not arrive in our 1963. They arrive in a new branch that splits from our timeline at that moment. Their presence affects that new branch, not ours. We continue in our original branch, unaware that countless alternate 1963s are being created constantly by temporal visitors we will never meet. The many-worlds solution also raises profound questions about personal identity that philosophers have debated since Everett first proposed the interpretation. If you travel to the past and create a new branch, which version of yourself is the real you? The version who grew up in the original branch and departed in the time machine, or the version who exists in the new branch you created? Both versions are physically identical at the moment of branching. Both have the same memories, the same personality, the same sense of being a continuous person with a continuous history. Both would claim to be you if asked. Both would be right in some sense, but they exist in different branches of reality that can never interact again. Are they the same person or different people? Some philosophers argue that branching timelines make personal identity incoherent as a concept. You cannot be the same person before and after time travel if time travel moves you to an entirely different branch of reality. The pre-travel and post-travel versions of yourself are as separate as identical twins. They share a common origin and identical genetics, but they are distinct individuals living distinct lives in distinct realities from the moment of branching onward. This has troubling implications for the ethics of time travel. If you travel to the past to prevent a tragedy, you do not actually prevent it for the people who originally suffered. You create a new branch where alternate versions of those people do not suffer. The original victims continue to exist in the original branch, their suffering unchanged. Have you done something morally good? Or have you merely created copies of people and given the copies better lives while abandoning the originals to their fates? The many worlds interpretation also has implications that extend far beyond the specific problem of time travel. If every quantum event creates new branches, then the total number of branches is inconceivably vast and growing exponentially every instant. Every possible outcome of every quantum event exists somewhere in the branching structure. Every alternate history that could have occurred according to the laws of physics does occur in some branch. This means that somewhere in the many worlds structure, versions of you made every different choice at every decision point in your life. Versions of you succeeded where you failed and failed where you succeeded. Versions of you chose different careers, married different people, lived in different cities. Versions of you died young in accidents that you narrowly avoided. Versions of you never existed at all, because tiny quantum fluctuations in your ancestors' biology led to different combinations of genetic material, producing different children or no children at all. Every path your life could have taken exists as an actual path travelled by some version of you in some branch. The choices you agonized over were all made both ways. The regrets you carry are balanced by branches where you made different decisions. The accomplishments you are proud of are matched by branches where you failed to achieve them. Does this diminish the significance of your choices? If every choice is made, every way somewhere in the branching structure, does choosing one option over another matter at all? Philosophers disagree sharply on this question. Some argue that your choices still matter to you in your branch, even if alternate choices matter to alternate yous in alternate branches. Others argue that the many worlds interpretation renders choice itself meaningless, because every option is taken, regardless of what you decide. The many worlds interpretation is not universally accepted among physicists, despite its mathematical elegance and its ability to resolve certain puzzles in quantum mechanics. Many physicists prefer interpretations that do not require the existence of countless unobservable alternate realities. The Copenhagen interpretation, for all its problems with the measurement process, at least describes a single reality that we can observe and test. The many worlds interpretation describes an infinity of realities, almost all of which are permanently beyond our ability to detect or verify. But the interpretation makes consistent mathematical sense. It resolves the measurement problem in quantum mechanics without requiring wave function, collapse, or special roles for observers. It remains one of the serious contenders for our best understanding of quantum reality. Several surveys of physicists have found it to be the second most popular interpretation after Copenhagen, and some surveys have found it to be the most popular among physicists who specialize in quantum foundations. If many worlds is correct, then backward time travel does not change the past. It creates alternate presents, branching from past moments. The grandfather paradox dissolves into a proliferation of timelines where every possible outcome occurs somewhere. Causality becomes a local phenomenon within each branch, rather than a global constraint across all of reality. Paradoxes are not forbidden. They simply cannot occur because every intervention creates new branches rather than modifying existing ones. But suppose the many worlds interpretation is wrong. Suppose there is only one timeline, and backward time travel really would return you to your own singular past with all the paradoxical implications that entails. How might the universe prevent the logical contradictions that would otherwise result? Stephen Hawking's chronology protection conjecture proposes that unknown physical mechanisms prevent closed time-like curves from ever forming in the first place. The universe does not permit time machines because time machines would create paradoxes, and paradoxes cannot exist. Therefore, some physical law or combination of physical laws must make backward time travel impossible, regardless of what Einstein's equations seem to allow. Hawking suggested several mechanisms that might provide chronology protection. Quantum effects might destabilize any forming time machine before it could be used. As a closed time-like curve begins to form, virtual particles from the quantum vacuum might accumulate in the region, creating infinite energy densities that destroy the structure. The energy required for time travel might concentrate so intensely that it collapses into a black hole that swallows the time machine before any traveler can pass through. The chronology protection conjecture has appeal because it preserves our intuitions about causality and free will. If backward time travel is simply impossible, we do not need to worry about paradoxes, predetermined fates, branching timelines, or any of the other disturbing implications we have examined. The arrow of time points firmly in one direction and cannot be reversed. The past is gone. The future is open. Our choices matter because they determine which of many possible futures becomes actual. But the chronology protection conjecture is just that, a conjecture. We have no proof that chronology protection exists. We have no confirmed mechanism that would provide it. We have only the observation that we have not encountered time travelers from the future, and the theoretical argument that paradoxes should be impossible in a logically consistent universe. The absence of time travelers from the future is often cited as evidence that backward time travel will never be possible. If time travel will ever become possible at any point in the future, we should expect travelers from that future to appear in our present. The technology exists in their time. Our era is historically significant enough to attract curious visitors. Yet we see no confirmed evidence of temporal tourists. Therefore, the argument goes, backward time travel must be impossible. But this argument has several weaknesses that prevent it from being conclusive. Perhaps time machines can only travel back to the moment when the machine was first activated. The physics of some proposed time machines has this property. A wormhole converted into a time machine through relativistic time dilation can only connect 2 points that both occur after the wormhole was created. You cannot use such a device to visit any era before the device existed. If this limitation applies to all possible time machines, then no time travelers visit our present because no time machine exists yet that would permit travel to our era. Once humanity builds the first time machine, travelers from our future could visit any moment after the machine's activation, but they could never visit 1963 or 1812 or any other historical date. Those eras are permanently off limits because no time machine existed then. Or perhaps time travelers do visit our era but conceal their presence carefully. Such a civilization might possess technologies that make perfect concealment trivial. They could observe our era without revealing themselves. They could interact with our world without leaving detectable traces. We would have no evidence of their presence if they chose to remain hidden. Or perhaps backward time travel is possible, but extremely rare and expensive. Perhaps building a time machine requires resources that only the most advanced civilizations can accumulate. Perhaps operating a time machine requires energy that makes each journey enormously costly. Under these conditions, only a handful of travelers might ever visit any given era. They might choose destinations of greater historical significance than our particular moment. The absence of obvious time travelers in our present would not prove that time travel is impossible, only that we are not an interesting enough destination to attract the limited number of temporal tourists. These possibilities might seem like excuses, ways to preserve the possibility of time travel despite the absence of any evidence for it. In science, absence of evidence is not the same as evidence of absence. We cannot prove time travel impossible merely by noting that we have not seen time travelers. But absence of evidence does not constitute positive support for a hypothesis either. The chronology protection conjecture remains unproven. But so does the possibility of backward time travel. Neither position can claim experimental verification. What does all of this mean for free will? The implications vary dramatically, depending on which resolution to time travel paradoxes we accept as correct. If backward time travel is impossible, blocked by chronology protection or some other mechanism, then free will operates more or less as we intuitively believe. The past is fixed because it has already happened. Nothing can change what occurred. The future is open because it has not yet been determined. Many possible futures exist as potentials, and our choices help determine which potential becomes actual. Our decisions matter because they causally contribute to the unfolding of events. This is the most comfortable resolution from the perspective of human agency and moral responsibility. We are responsible for our choices because those choices have real effects on a genuinely open future. We deserve credit for good choices and blame for bad ones because we could have chosen differently. The past constrains the present, but the present does not constrain the future. Time flows in one direction, and we ride that flow, making decisions that shape what happens next. If the Novikov self-consistency principle is correct, then free will operates within constraints that we may not notice but cannot escape. We can choose freely within the set of actions that produce self-consistent timelines. We experience ourselves as having many options, but only some of those options are genuinely available. We cannot choose actions that would create paradoxes, not because some force physically prevents us, but because paradoxical choices are not genuine possibilities to begin with. This is a more troubling picture because it suggests that the appearance of freedom might exceed the reality of freedom. You feel that you could choose to create a paradox. You feel that pulling the trigger to kill your grandfather is a genuine option that you could select if you wanted to. But under Novikov's principle, that feeling is an illusion. You could not choose to create a paradox any more than you could choose to draw a square circle. The option appears available, but is actually undefined. How would this constraint feel from the inside? Presumably, it would feel exactly like the experience we already have of making choices without creating paradoxes. We never attempt backward time travel, so we never encounter the constraints that would prevent paradoxes. If we did attempt such travel, we would find ourselves unable to create contradictions, but we might not recognize this inability as a cosmic constraint rather than ordinary bad luck or change of heart. If the many worlds interpretation is correct, then free will takes on a strange new meaning that challenges everything we think we understand about choice and consequence. We choose freely in the sense that every choice we might make does occur in some branch. Every option is selected. Every path is taken. No possibility is excluded by our decision-making, because all possibilities are realized somewhere in the branching structure. But we do not control which branch we experience. We cannot choose to be in the branch where we selected option A, rather than the branch where we selected option B. Both branches exist. Both contain versions of us who made different choices. Our sense of having chosen one option over another is accurate for our branch, but alternate versions of ourselves made alternate choices in their branches, with equal reality and equal claim to being us. Does this mean our choices matter? In one sense, yes. The choice you make determines which branch you experience going forward. Your life unfolds according to your decisions within your branch. But in another sense, no. Every choice is made. Every life path is followed. The branching structure contains all possibilities, so no individual choice excludes any possibility from existing somewhere. If the block universe is correct, and past, present, and future all exist simultaneously as a four-dimensional structure, then free will might be entirely illusory. Our sense of making choices would be a subjective experience, embedded in a structure where every event is as fixed and eternal as every other event. Both would simply exist as different temporal locations within the unchanging block. In the block universe, the feeling that the future is open and the past is closed would be a perceptual artifact of consciousness, moving through time, not a feature of temporal reality itself. Your future is already there, already determined, already as real as your past. Your sense that you are deciding what happens next would be analogous to a character in a novel, feeling that they are choosing their actions, when in fact the story is already written and their actions are already fixed on the page. This is perhaps the most troubling implication of the physics of time for human self-understanding. The mathematics of relativity supports the block universe interpretation more strongly than most physicists are comfortable admitting publicly. Nothing in fundamental physics distinguishes past from future or privileges the present moment as specially real. The arrow of time appears nowhere in Einstein's equations or in the standard model of particle physics. The distinction between past and future emerges only from thermodynamics, from the statistical tendency of entropy to increase, from the expansion of the universe from low entropy initial conditions after the Big Bang. But thermodynamics is emergent from more fundamental physics. It describes statistical regularities rather than fundamental laws. The arrow of time is not written into the foundations of reality. It arises from boundary conditions and statistical mechanics. Some physicists argue strenuously that the arrow of time is fundamental, despite not appearing in the equations, that the past is genuinely gone and the future genuinely open, that the block universe interpretation misreads the physics. But this view requires adding something to the mathematical framework that the equations themselves do not contain. It requires asserting that there is a special now that moves through time, converting indeterminate future into determinate past. And there is no physical evidence for such a moving now. No experiment has ever detected it. No equation requires it. This brings us to the deepest and most disturbing truth that the physics of time travel reveals about reality. We do not understand time. Not really. Not fundamentally. After more than a century of relativistic physics, after thousands of experiments confirming time dilation to extraordinary precision, after decades of serious theoretical work on closed time-like curves and their implications, we still do not know what time actually is. We have equations that describe how time dilates with velocity and gravity. We can calculate these effects to many decimal places. We can build GPS satellites that would fail without relativistic corrections. We can observe muons surviving their journey through the atmosphere because their internal clocks run slow. The mathematical framework is solid and well confirmed, but we do not know what time is. We do not know why it appears to flow from past to future. We do not know why we remember the past but not the future. We do not know why entropy increases in one temporal direction rather than the other. We do not know whether the past and future exist as robustly as the present, or whether only the present moment has genuine being. These are not scientific questions we are close to answering. These are mysteries that deepen the more carefully we examine them. Every proposed answer creates new puzzles. Every framework that resolves some questions raises others equally profound. Time travel forces these questions into sharp focus because it makes us confront what would happen at the boundaries of temporal experience. If you could travel to the past, what would you find there? A place as real as the present, populated by people as conscious as you? Nothing at all, because the past no longer exists as a destination you could visit. If you could travel to the future, what would you find? Events that have already been determined, written into the block universe and simply waiting for you to arrive at their coordinates, probabilities hovering in superposition, waiting for your observation to collapse them into definite outcomes. A void waiting to be filled by choices not yet made, decisions not yet taken, events not yet occurred. We do not know. We cannot know, not with our current understanding of physics. Time remains the most mysterious aspect of physical reality. It is the dimension we experience most intimately, the medium through which all our experiences unfold. Yet we understand it less completely than almost any other aspect of the physical world. The paradoxes of time travel are not just logical puzzles that philosophers invented to torture physics students. They are windows into the inadequacy of human intuition when confronted with the true nature of temporal reality. We evolved to track sequences of events, to remember what happened, to anticipate what might happen. These capacities served our ancestors well on the African savanna. They help us navigate daily life effectively, but we did not evolve to understand what time itself is. We did not evolve to comprehend whether the past still exists, or whether the future is already determined. We did not evolve to grasp what would happen if causal loops closed or timelines branched. Our intuitions about time are tools for survival, not instruments for metaphysical truth. Perhaps some future physics will resolve these mysteries. Perhaps a theory of quantum gravity will explain precisely why closed time-like curves cannot form, vindicating Hawking's chronology protection conjecture with mathematical rigor. Perhaps new experiments will demonstrate that the block universe interpretation is wrong, that the future really is open in some physically meaningful and measurable sense. Or perhaps we will build time machines and discover through direct experiment what logic and theoretical physics cannot tell us with certainty. Perhaps the paradoxes will resolve themselves when we actually attempt backward time travel and observe what happens. Perhaps the universe will surprise us, as it has so many times before, with behavior that no theorist predicted and no philosopher anticipated. Until then, time travel remains what it has always been: a boundary where confirmed physics meets logical paradox. A frontier where mathematical possibility confronts intuitive impossibility. A mirror in which the nature of reality reveals its deepest mysteries while refusing to yield clear answers. You are still traveling through time right now, as you have been throughout this exploration, 1 second per second, moving forward into a future that may or may not already exist, leaving behind a past that may or may not still be real. The clocks around you tick at slightly different rates depending on their altitude and motion. Satellites overhead age differently than clocks on the ground. The physics of time dilation is confirmed beyond any reasonable doubt. But whether you could ever reverse direction, whether you could ever return to yesterday, whether the past is a destination you might someday visit or merely a memory you carry forward, these questions remain open. The paradoxes remain unresolved. The nature of time remains unknown, and perhaps that is the most disturbing realization of all. Not that time travel is impossible, not that it creates paradoxes, but that after more than a century of relativistic physics, after countless experiments confirming time dilation, after decades of serious theoretical work on the nature of time, we still do not know whether the past is somewhere you can go or merely somewhere you have been. We do not know whether the future is determined or open. We do not know whether free will is real or illusory. We do not know what time is. The paradox that breaks our brains is not the grandfather paradox. It is not the bootstrap paradox. It is not the predestination paradox. The paradox that breaks our brains is the paradox of time itself, a phenomenon we experience every moment of our lives, a dimension through which all our experiences unfold, and yet we understand it less completely than almost any other aspect of physical reality. Forward time travel is confirmed. We do it constantly, and we could do it dramatically with sufficient velocity or gravitational intensity. Backward time travel remains a question mark, permitted by some equations, prohibited by some interpretations, paradoxical under almost any consistent logical analysis. We are prisoners of the present moment. We can move forward into the future at rates determined by our velocity and our gravitational environment, but we may be forever barred from returning to the past. Or we are travelers through a 4-dimensional block universe where past and future both exist eternally and only our consciousness creates the illusion of temporal flow. Or we are the inhabitants of one branch among infinitely many in a vast multiverse, each making choices that spawn new timelines while leaving original timelines unchanged. We do not know which of these descriptions is correct. We may never know. Time keeps its secrets, flowing forward through every experiment we conduct to understand it, never revealing whether the flow is real or whether the flow is an illusion created by minds that evolved to survive rather than to comprehend. The universe permits us to dilate time. It permits us to age slower than those we leave behind. It permits us to jump forward through decades or centuries at the cost of leaving everything we knew in an unreachable past. These capabilities are confirmed physics, waiting only for engineering advances that may come in decades or centuries or never at all. But the universe guards its deepest secrets about backward travel. The equations permit it in some theoretical frameworks. The paradoxes seem to forbid it logically. The protection mechanisms remain hypothetical, and the fundamental nature of time itself, the question of whether the past still exists to be visited, remains as mysterious as it was when Einstein first discovered that time itself is relative. This is the truth about time travel that will break your brain. The brain-breaking truth is that after everything physics has taught us, we still do not know what time is. We still do not know whether the past is real. We still do not know whether the future is fixed. We still do not know whether our choices create tomorrow, or merely reveal what was always going to happen. We are time travelers in the most fundamental sense. We are carried forward one moment at a time through a dimension we do not understand. We cannot stop. We cannot reverse. We cannot even know for certain whether our journey has a direction or whether that direction is merely an illusion crafted by consciousness to make experience coherent. The paradox is not in the physics. The paradox is in time itself, and that paradox remains unsolved.